Hello students, welcome to IMS GATE Academy. I started electronic devices and circuits in the foundation course. I have done so far insulator, conductors. Today I would like to start semiconductors. It is very important for EC students particularly. So each and every information regarding the what now semiconductors you are going to get now. Yes, I will start then. Semiconductor. Semiconductor. But an insulator means I defined the material which does not allow electrons to pass through it. But depends upon what factor we can say it doesn't allow the current to pass through it. Based upon the concentration, we can classify the material. I said already, insulating materials are going to have the concentration of electrons less than 10 power 5 per cm cube, I said now. But if it is taken for the conductor, 10 power 21 per cm cube, I said now. If the concentration lies in between 10 power 5 to 10 power 21 per cm cube, you think it's so. In that case, the material can act as a semiconductor. That is semiconductor only you can say. So how we can define exactly definition of the semiconductor? The material which lies in between the properties of insulator and conductor is called as a semiconductor only now. The fourth group elements exactly we can say it as a what now? Semiconducting material only now. In the periodic table, fourth group elements only now. What are the fourth group elements? Fourth group elements means what is the meaning? The valence electrons of any atom, valence electrons of any atom are 4, then we can say it is a fourth group element only now. Silicon, germanium, carbon, all these will come under the fourth group only we can say. But carbon cannot be considered as a what now? Semiconducting material. So germanium and silicon can be taken as a what now? Semiconducting material only now. Carbon comes under the what? Insulating material only now. Understand now. But anyhow, the semiconductor, if it is taken here as germanium and silicon, I said now, examples, I say it now. How many types of semiconductors are there? There are two types of semiconductors, I can say. One is said to be intrinsic semiconductor. Second one is said to be extrinsic semiconductor. I said now, first we can define the semiconductor. Definition I will give now. The material which lies in between the properties of insulator and conductor is called as semiconductor. Like that you can define. But what are the example means? I said germanium or silicon we can take now. Examples are nothing but germanium, silicon only. Most practically we are using silicon only now. It is silicon we are using practically as compared to the germanium only we can say. The reason is what? The silicon can have the high withstanding temperature only we can say now. But in the germanium cannot withstand high temperature only now. Understand now. When the high temperature it is not maintained means what happens now? It is going to develop it is going to break the bonds and easily it can allow the reverse saturation current in the what? Germanium. But silicon can withstand the high temperature. That's why we are using the silicon only we can say. But what are the two types of the semiconductors? There are two types of semiconductors we know. there are two types of semiconductors. There are two types of semiconductors. I can write here. There are two types of semiconductor. One is nothing but intrinsic semiconductor. Intrinsic semiconductor I can write. Second one is said to be extrinsic semiconductor. Extrinsic semiconductor I can write. Extrinsic semiconductors. So like that we can divide. SC means a semiconductor only you can say. Initially I would like to take intrinsic semiconductor. The first one is intrinsic semiconductor. Intrinsic semiconductor. But how that energy band diagram? The energy band diagram of intrinsic semiconductor will be like this. The energy gap is very, very small in intrinsic semiconductor. We cannot find more only now, very small. This is the valence band. This is said to be conduction band only now. This is forbidden energy gap. Forbidden energy gap. This can be taken here now. But when we can say the given material is intrinsic semiconductor, the pure type of semiconductor is called as an intrinsic semiconductor. The pure form, if you got semiconductor, then it is called intrinsic semiconductor. If the atomic arrangement inside of the intrinsic semiconductor is observed, identical atoms only we can find. All are identical atoms. Similar atoms only we can find. That is nothing but intrinsic semiconductor only now. Thus we can define the pure type of semiconductor. A pure type of semiconductor is called intrinsic semiconductor. We can define like this. A pure type of semiconductor. I am putting semiconductor SC. A pure type of semiconductor is called intrinsic semiconductor. Intrinsic semiconductor we can call. But example same I said no, germanium and silicon only now, understand now. But in this intrinsic semiconductor, concentration of electrons and concentration of the holes will be same only possible. That means whatever not the but second point we can say electrons and holes concentration are same. N and P are equal. Concept, but in intrinsic semiconductor, concentration of electrons and holes are equal. Both are equal only now. We can find both are equal only here now. Both are equal means what is the meaning? That means from the, but already the valence band will be filled with what? Electrons only, no doubts. The electrons which are in the valence band are said to be bounded electrons also we can call exactly, bounded electrons only now. At 0 Kelvin, catch my point, at 0 Kelvin, all the electrons are existing in the valence band only now. They will not be free. We cannot find any number of electrons in the conduction band. How many number of electrons are existing in the conduction band at 0 Kelvin? Suppose you are asking means you can say directly, 0 number of electrons are existing in the conduction band. At a room temperature means what now? 300 Kelvin. At room temperature, what is going to happen now? At room temperature, the electrons will be liberated from the what now? Valence band. We don't need to give. The temperature is maintained in the atmosphere, 300 Kelvin you think it's so. Immediately electrons will be liberated from the valence band. Once the electrons are released, otherwise it became free from the valence band, directly they will enter into the what now? Conduction band only now. how many number of electrons are reaching to the conduction band? How many number of electrons reaching to the conduction bands is equal to the what now? Number of holes generated in the what now? Valence band only now. That means, for example, here certain number of electrons are reached. Suppose I have taken here the certain number of electrons are reached that many. That many number of the holes will be generating here now. That many number of the holes are generated only, you can say. That means once the electron is reached to the conduction band, you think it's so. Once the electron is free from the what now valence band, you think it's so. Thereby generated one hole. One hole is created. Hole means what is the meaning? A lack of electron is said to be what now? Hole only now. Once the electron is moved, thereby creating a vacancy. That vacancy we can call it as a hole only, we can say. That is a hole only now. That's why the vacancy created by the what now? Lack of electrons is said to be hole. We can define only now. Understand now. So now you watch the valence band what now contains number of holes denoted by symbols P. Number of electrons can be denoted by letter N. I said here now, in intrinsic semiconductor, concentration of electrons and holes are equal, I said now. That is what N equal to P we can find. Concentration of electrons and concentration of the holes are equal only now. Why particularly we are selecting the what now? Semiconducting materials in the electronic devices. That is very important now. Why it is selected means, but you try to take at 0 Kelvin. At 0 Kelvin, if you watch, can you find any number of electrons in the conduction band? We cannot find. No electrons we can find in the conduction band only now. Whenever no electrons we are finding in the conduction band, what is going to happen now? The material can act as an insulating material only now. It doesn't allow any conduction, even you are applying the any potential only now. Understand my point now. But at room temperature, atmospheric temperature is a 300 Kelvin. You don't need to give any supply. Without what now giving the any supply, you can find what now number of electrons to be existing in the conduction band only now. Because thermal energy which is in the atmosphere only can make the what now electrons to liberate. And it allows to reach to the conduction band only now. That means at room temperature, we are finding the concentration of electrons the more in the conduction band only now. Once the electrons are existing in the conduction band, what is going to happen now? You connect now supply. You connect a supply to the intrinsic semiconductor. Immediately what is going to happen now? The electrons which are in the conduction band will be excited and they will try to move to the front only now. Due to flow of these electrons, current is going to flow in the intrinsic semiconductor only now. That's why, is it required high potential or low potential to allow the current to flow in the what now? Intrinsic semiconductor. Less potential is enough, because the potential is only for what now? Pushing the electrons, to move the electrons in the conduction band only, you can say, to make the conduction only now. That's why the external force which is required for intrinsic semiconductor is a very less only now. Understand my point now. But that's why we are selecting the semiconducting material. At room temperature itself, we are finding the what now? Electrons concentration in the conduction band. So without giving the any potential, directly we are getting the electrons. Then even a less potential you applied, current flow is possible in the intrinsic semiconductor. That's why you can say the flow of current is possible. This point we can put now. The flow of current is possible. The flow of current is possible in intrinsic semiconductor. ISC I have taken out, intrinsic semiconductor. Even if less voltage is applied externally, even if a less potential is applied, less potential is applied externally. That point is very important. Externally. That's mostly possible. But one more point you have to understand here now. Any semiconducting material, if it is taken, what type of bond it is going to exist? What type of bond is going to exist? I'm not asking the band. Band is a valence band, conduction band, and forbidden band also we can say. I'm saying what type of bond. Bond means the different types of the bonds we can find. One is a covalent bond, second is an ionic bond, third one is a metallic bond, like that you can have here now. But what type of bond is going to bond is existing in the what now semiconductors means covalent bond is going to exist only we can say. How the covalent bond is going to be formed? Whenever the sharing of electrons are taken place in between any two atoms, you think it's so, thereby creating the what now covalent bond only now. That's why in the crystal structure of intrinsic semiconductor, you can find the sharing of electrons between two atoms only, you can say. Due to sharing of those what now valence electrons, it is going to form the covalent bonds only, you can say. So what we can say, what type of bond is existing in the what now? These semiconductors, if you are asked, you can say directly, it is a covalent bond only, we can say. Understand now? But ionic bond means it is entirely different. That means what due to transfer of electrons from one atom to the other atoms, it is taken place, you think it's so. The time it is going to form the ionic bond only now. Here we cannot find any transfer of electrons from one atom to the other atom only now. Here only sharing of electrons are done. Sharing of electrons means the sharing between the two atoms, how it is taken place. Each and but suppose you have taken two atoms, two similar but here mostly similar, but a covalent bond also forming in between the two similar atoms only you can say. But semiconductors contains identical atoms only now. They are nothing but the all are silicon atoms only, similar size only now. Similar atoms only you can find now. Similar atoms whenever you brought very close together, thereby forming the covalent bond. In that process, what is going to happen now? Each atom is going to contribute equal number of electrons. Suppose one atom is contributing the one electron you think it, so other atom also can contribute the same one electrons. So the addition of these two electrons, one and one is nothing but the two electrons will become now. Those two electrons will be shared by the both atoms only now. That in that case, it is going to form the covalent bond only we can say. Suppose you have taken ionic bond means what I said now, due to transfer of electrons from one atom to the other atom, it is going to form the but the ionic bond only now. That bond will not be created here now. But if it is taken the conductors, what type of bonding is going to exist? What type of bonding is going to exist in the conductors? That is a metallic bonding only now. Due to metallic bonding, what happens now? Conductors are going to exist only now. There is an entirely different matter now. I am not going to discuss about that now. Understand now. Anyhow, here what bond is existed means covalent bond only it is existing. For example, you have taken the you applied the temperature, you maintain the temperature of 0 Kelvin for example. When the 0 Kelvin is applied means, but all the electrons are said to be bonded electrons only. All the electrons are bonded electrons means what is the meaning? At 0 Kelvin, all the electrons are existing in the valence band you will say. Otherwise you can say one more way also. Sorry. All the electrons are existing in the bond only now. In the covalent bond only it is existing means we can say bonded electrons only. Catching my point now. Bonded electron indicates electrons are existing within their bond, covalent bond only now. But once the temperature is applied, room temperature whenever you applied, at the time what I said now, electrons are liberated I said now. That means bond is broken down. Once the bond is broken down, electrons becomes free. Once the electron came outside of the what you can say, the bond, what is going to happen now? In the bond, once the bond is broken down by the breaking of the when releasing of the electron, you think it's so, thereby creating a hole, due to lack of that electron only now. Understand now. Anyhow, what I can say now, covalent bonds are existing in this particular intrinsic semiconductor. I said here now. Understand my point now. But based upon this intrinsic semiconductor, from this intrinsic semiconductor, I would like to give certain points also now. What those points means, you watch it now. What I want to give certain mathematical formulas also I would like to explain in the intrinsic semiconductor, what they are. Current density in semiconductor I want to give here now, because to do the problems based upon these semiconductors, we need to know this formula. Current density in intrinsic semiconductor, ISC I have taken now, intrinsic semiconductor. The current in the current passing through the intrinsic semiconductor is nothing but due to flow of electrons and holes also. Both will try to flow only now. Here I can say the total current density in intrinsic semiconductor, I would like to take it as a what now? Current density due to electrons, Jn plus current density due to holes, Jp you have to take. But already current density due to the electrons, Jn I gave it. Where I gave? In the conductors I gave it now. Same formula applicable. There we are using concentration of Nn. But in the case of what? Jp means the holes concentration we have to include only now. In the place of N, I can put the P. Rest of terms will be same only now. I say J equal to, I can note down, current density in the N-type semiconductor is nothing but N into Q into mu N into, mu means mobility of electrons, into E only now. N means concentration of electrons, Q is the charge of electrons, and mu N is nothing but the mobility of electrons, E is nothing but the electric field intensity only now. What about the Jp? Jp equal to what? N equal to, in the place of N, I can put as a P. P into Q into mu P into E I can put now. P means concentration of holes, mu P means mobility of electrons. Q we know very well, charge of electron. Charge of the what now? This hole only now. E equal to electric field intensity only we can say now. Anyhow, this is required now. And here I said already, in intrinsic semiconductors, I said already, concentration of electrons and concentration of the holes are equal, I said already. N equal to P. N equal to P. That N equal to P, that equal to I have taken Ni is the symbol I introduced. Concentration of electrons equal to concentration of holes, that equal to I have taken one Ni symbol. What is that Ni, sir? Ni equal to, I want to give the name of intrinsic concentration, where Ni equal to N suffix I is intrinsic concentration. Intrinsic concentration, it is given symbol. Intrinsic concentration, I want to give the symbol only now. So N equal to Ni, I can put P equal to Ni also, I can put here now. Now I can write the total current density, I can write in the form of what? N equal to Ni and Q into mu N into E. The concentration of the holes is nothing but the P equal to Ni. That equal to what? Q into mu P into E I can write here now. The finally current density equal to what formula you can use in the problems? Ni is taken common, Q is taken common, E is to be taken common, mu N plus mu P you can get now. Yes, the formula you must remember to do any problem to determine the current density in intrinsic semiconductor. What are the units of current density? Already I gave it. Current density equal to current by area. Current is in amperes. Area is nothing but the cm square. Otherwise, amperes per cm square or amperes per meter square also you can write now. So units I can write amperes per cm square or amperes per meter square also we can write it now. That is allowed now. That is the total current density you can use now. But sometimes it comes a necessity to find out the conductivity in intrinsic semiconductor. What formula you can use? Just I will give the explanation for that. You can get the idea about this and stand up. But mostly in the what now? Electronic devices, formula should not be given directly only now. If the formula is given directly means concept is not available only now. Just what now? Wherever simple analysis is there, that we have to do only now. Understand now. The next one, conductivity in intrinsic semiconductor. But after giving all these formulae, then I will start the problems also. Conductivity in intrinsic semiconductor. I said already, conductivity in what a current density in semiconductor is nothing but the current density due to electrons and current summation of the what now current density in current density due to electrons plus current density due to holes I have taken both. In the same way, total conductivity you can determine by adding the what now conductivity due to electrons and conductivity due to electrons also, holes also then answer. I say what I say, the total current density, total conductivity in intrinsic semiconductor, sigma I want to denote. This is equal to conductivity due to electrons plus conductivity due to holes. We can note down here. We know very well in the conductors I explained what is the conductivity. What is the conductivity definition? I gave it in the what now? Conductors. It is the product of charge density and mobility. I gave it already. Charge density means what I said now, the product of what now, concentration and also what now, charge I gave it, N into Q I gave already. Now here also I can put directly here now. The conductivity in intrinsic semiconductor I can find conductivity equal to charge density, NQ into what, mobility. Charge density into mobility of electrons thereby required for electrons. If it is for the holes, what I can write in the place of N, I can put a P into Q into mu P, I can use directly. P into Q, P into mu P will know. I said already, in intrinsic semiconductors, concentration of electrons and concentration of the holes are equal. Those two are equal. So I can put N equal to P, P equal to Ni also I can put now. Ni is nothing but the intrinsic concentration, I said already now. So I can write here for intrinsic semiconductor, N equal to P, that equal to Ni, we know very well. I can write the conductivity in intrinsic semiconductor is nothing but N equal to Ni into Q into mu N. I can write P is nothing but the Ni into Q into mu P. I can write. I can take in common. What are the terms we can take common here now? So Ni into Q can be taken common. Finally, I can get mu N plus mu P only now. So the formula we are going to use to find out the conductivity in intrinsic semiconductor. What units we can give for the conductivity? Already I gave it, mho per centimeter it is allowed. Mho per centimeter is accepted. Or mho per meter also it is acceptable. This is the unit of conductivity only now. Sometimes in the problems it comes a necessity to find out the resistivity also. Resistivity equal to what you can say? It is the, already I gave it, it is the reciprocal of conductivity only now. Conductivity we know, just we can get from that easily formula we can create. How we can create formula for the resistivity? Resistivity in intrinsic semiconductor. In intrinsic semiconductor, resistivity is denoted by symbol rho. Otherwise, you can define it first, then after I will do clearly now. How we can define? It is the reciprocal of conductivity. It is the reciprocal. It is the reciprocal of conductivity. It is the reciprocal of conductivity, we can write directly. That I can take rho equal to, I can note down 1 by sigma I. The resistivity for intrinsic semiconductor, I will put at the suffix I. So we got already sigma I, what I got it? Ni into Q into mu N plus mu P, already given. We got already. That formula you can use for the resistivity. This formula, already I gave it, where I gave that formula? Ni into Q into mu N plus mu P. That formula only I gave it here. So this is the information is required regarding the intrinsic semiconductor. Now I would like to do the problems based upon this formula only now. Yes, we can start the problems based upon, and also some more points also I want to give here now. I would like to give few more points. And also we can define one more way also here now. Here the Ni into Q into mu N plus mu P means, please watch it. Current density equal to, we got here now, Ni into mu N plus mu P into Q is nothing but what I said now, sigma I gave it now, sigma suffix C. There's a current density, one more formula you can create here now. What formula you can create? Ni into Q into mu N plus mu P, just now I gave it sigma I. Sigma I into E also we can write now. That's why we can write here clearly. Now I can write current density can also be written by J, can also be written sigma I into E, it is allowed. That also allowed only now. This is that way it is possible. Followed my points. And what are the units is possible for the what now resistivity here? Ohm centimeters it is allowed. Ohm centimeter allowed, or ohm meter also acceptable. These are all required only, we can say. Understand that now. The next one. But how the concentration can be taken here now? Suppose I have taken here one silicon. This is nothing but the germanium I have taken here now. This is germanium. But the general values I want to give now. At room temperature, what are the values now? At room temperature, I am giving here now. At room temperature, suppose the Ni value we are having now, intrinsic concentration. Intrinsic concentration is 1. For silicon, 1.5 into 10 power 10. 1.5 into 10 power 10 per cm cube, mostly possible. General values. I am giving the general values of Ni. 1.5 into 10 power 10 per cm cube. At room temperature only it is possible. At room temperature. If it is a silicon, you think it's so. Then you can have 2.5 into 10 power 13 per cm cube, it is possible. These are all at room temperature I can write. At room temperature I am giving. Understand? These values you have to remember only, you can say. But when the temperature is changing, you think it's so. All these parameters are getting changed also now. Understand? If it is a mobility of electrons, how much? What is mobility of electrons for silicon at room temperature? Mu n is nothing but 1300. 1300 cm square per volt second. Cm square per volt second I can write now. These are all fixed values, you must remember. Cm square per volt second we can put now. But at room temperature, mobility of electrons for silicon I gave it now. And also for germanium, this is the mu n for the what no, for germanium can be taken 3800 cm cube, that is cm square per volt second, it is possible. That means the mobility of electrons or Ni value will be changing based upon the what type of material and also what no, room temperature only, temperature only now. Based upon the temperature, variation of these values possible. Understand now? But the Ni value depends upon what factors? Two factors just now I said now. From that point, you can understand. Intrinsic concentration depends upon the two factors. One is the temperature, second one is nothing but the type of the material only now. But that value you can get from the manual only now. In the manual you can find the material is a germanium. The temperature is what? 300 Kelvin. Directly from the what now manual onwards, that value can be taken only now. For any temperature from the manual you can get the what now? Ni value only now. But these are all the what now at room temperature only now. Understand now? But suppose mobility of holes for silicon is nothing but, for silicon is 500 cm square per volt second it is maintained. If it is a germanium, you think it's so 1800. These are all fixed values. 1800 cm square per volt second. Cm square per volt second is possible now. But these are all the fixed values I said already. Atomic density means what? What atomic density you can find in the germanium and silicon? Sharply useful these also. Atomic density. Atomic density also very important. The 5 into 10 power 22. 5 into 10 power 22 atoms per cm cube possible. These many number of atoms are possible per cm cube. But if it is a germanium, you think it's so. At room temperature, atomic density is 4.5 into 10 power 22. 10 power 22 atoms per cm cube possible. Atoms per cm cube it is possible. Before doing the problems, these are all the informations, more important one we can say. Understand now. And one more point also very important here now. Okay, before that we can do certain problems better now. First we can do the certain problems, then after we can discuss the rest of things now. Yes, you take the first problem based upon this. The first problem is calculate, is asking to calculate resistance of, resistivity of pure germanium, resistivity of pure germanium pure germanium at room temperature, at room temperature, at room temperature, Ni equal to intrinsic concentration is given 2.5 into 10 power 13 per cm cube. Per cm cube it is given. Mobility of electrons given. Mobility of electrons given. Mu n equal to here given 3800 cm square per volt seconds. Cm square per volt second it is given. And mobility of holes also given here now. Mobility of electrons, mobility of holes are given. Mu p is given. Its value is given as 1800 cm square per volt second. Cm square per volt second it is given. Yes, that is a given problem only now. This is the given problem. How we can tackle this question? You please watch. What way we can tackle this question? Anybody can do? Every formula is given in your hand only now. Now doing this problem is not complicated. Very easily we can complete this question only now. Calculate resistivity of pure germanium. Resistivity means we know very well. We know very well. Rho value required. Resistivity of pure germanium is given clearly. The pure indicates intrinsic semiconductor only now. Intrinsic means rho I is very important for intrinsic pure germanium. But Ni is given, mu n is given, mu p is given. How we can find this? We know very well. Rho I equal to, we can write again, intrinsic, that equal to 1 by sigma I we know. Sigma I equal to, I gave already, 1 by Ni into Q into, what I gave it? Ni into Q into mu n plus mu p is given. Mu n plus mu p is given already. Already given that formula. By using this formula directly, you can determine the what now? Intrinsic resistivity of the what now? This pure germanium. I can find by substituting the values. 1 by Ni is given 2.5 into 10 power 13. The Q value we know very well, but we will not give in the problem only now. Charge of electron is 1.6 into 10 power minus 19. 10 power minus 19. Whatever the mobility of electrons, mu n is nothing but 3800. 3800, no doubt. Whatever the mobility of holes, they are given mobility of holes also here given. Mobility of holes given as 1800 here now. Use calculator, then you will get rho I equal to, if you are using the calculator, its value will come as a, but approximately 44.64 I think now. Approximate value I am giving now. You please try. If any changes means you make it, no problem. 44.64 ohm centimeters possible. If any changes means you can change, but the methodology is this only. Understand now. That way we can get the resistivity of pure germanium now. I think students followed clearly. Yes, I want to give the one more question in your hand, but I wish to give one more question now. Now you please try again this question. The next question here given is a pure silicon. A pure silicon. Yes, I have taken now silicon. Sample of length. Sample of length. Sample of length 10 centimeter. 10 centimeters. Sample of length 10 centimeter is given. And cross-sectional area. And cross-sectional area. And cross-sectional area. Cross-sectional area. The cross-sectional area is given 10 power minus 2. Ten power minus 2 is given here. 10 power minus 2 cm square it is given. Area is given 10 power minus 2 cm square it is given. And has Ni equal to, and has intrinsic concentration given here now. Ni is given. That is nothing but 1.5 into 10 power 10. 1.5 into 10 power 10 per cm cube. Per cm cube it is given. That is the intrinsic concentration had by the material only now. And also given mu n, mobility of electrons here given as 1300. 1300 cm square per volt second it is given. And the mobility of holes also given in the problem. Mobility of holes given as a 500 cm square, 500 cm square per volt second it is given, per volt second at room temperature. At room temperature it is given. At room temperature it is given. Is asking to calculate, but I will give the different parameters, not one question. More than one question I want to give now. Calculate resistance of sample, first question. Resistance of sample, I want. But I want the resistance of the sample. And second question which I want to give here is, the second question which I want to give here is, the second one I am asking now, current. I want current also. If electric field intensity, E, electric field intensity is given 20 volts per cm. 20 volts per cm applied, is applied. Yes, this is the given problem. By using the formulae I gave, anybody can do this question without my help? Without my help, anybody can complete this question? Ankit, hello. Yes, hello. Tell me, Ankit. Good afternoon, Ankit. Yes, I will do this question. Please watch. But the data regarding the what now? This problem is given here now. A pure silicon is specified directly in the problem. A pure silicon is specified. A pure silicon means what I can say here now, it is nothing but an intrinsic semiconductor. It is not extrinsic. 100% it is an intrinsic semiconductor. A pure silicon is specified in the problem. So I can apply the formula regarding the what now? The intrinsic semiconductor. Is asking to find the first question is the resistance is required. Is asking to find the resistance. Now first we can note down the data here what is given. It's given, Ni is given in the problem. I note down here 1.5 into 10 power 10 I gave it per cm cube I gave already. And also we got here in the problem mu n is given, area is given 10 power minus 2 already given cm square, and also length also given 10 centimeter in the problem. Catch once again, try to watch. The length is given 10 centimeter, area of the cross section 10 power minus 2 is given. I am putting those values. 10 centimeter is given. And mobility of electrons also I gave. Mu n is given in the problem. That mu n equal to what is given? That is given as a 1300 cm square per volt second. And a mu p also given in the problem. Mu p equal to, we can note down as a 500 cm square per volt second. Ni also given in the problem. Ni is already given. Yes, that's given already. No problem. Now we can start the work. What is the first question in the problem here? Is asking to find the resistance of the material. What material? For intrinsic semiconductor, we need to calculate resistance. We know very well resistance equal to what? Rho L by A. Rho L by A. I can write directly from the networks. Rho L by A is nothing but the resistance only. What rho is to be taken? That rho is nothing but for intrinsic semiconductor. Rho I will put. I indicates it is an intrinsic semiconductor only now. Then I can write what is the rho I. You calculate at first in the problem. Rho I is nothing but rho I equal to 1 by sigma I. I gave already. We know very well what is sigma I. 1 by Ni into Q into mu n plus mu p. That is already given. Formula is given to you. We know very well what is Ni is given, mu n is given, mu p is given, Q value we know. Then we can get directly what is rho I. How to get this rho I? Yes, I will find 1 by Ni equal to 1.5 into 10 power 10. The value of Q is nothing but charge equal to what? 1.6 into 10 power minus 19. And mobility of electrons, I can note down 1300 here. This is given 1300. Mu p is nothing but 500 here. Mu p is given 500 only now. If you are using the calculator, its value comes as, its value will be 2. This rho I is nothing but 2.31, approximately it comes 2.31 into 10 power 5. That value possible, ohm centimeters. This is the value possible for rho I, approximately. If any changes means you change that number, but values are same. Calculation, you watch it now. If you got same number, okay. If you got any other number means you put it, no problem. Understand? Approximately that value comes. Once you are getting the rho I, you can determine the resistance R. How you can find the resistance of intrinsic semiconductor? Rho I into, we got to say 2.31 into 10 power 5. Length is nothing but 10 centimeters only now. And also area is given 10 power minus 2 is given in the problem. 10 power minus 2 it is given. You can determine resistance R. Its value comes as 231 mega ohms. 231 mega ohms mostly it comes. That much resistance is possible. Otherwise, you calculate whatever the value you are getting, that you can put only now. That way, we can determine the what now? Resistance value. What about the next question? What about the next question is asking the problem? You check it. In the problem, first question is nothing but the resistance of the sample. We got it. Second one, I want current. Current is required. Current which is passing through the what now? Intrinsic semiconductor. If electric field intensity is at 20 volts per cm is given. If electric field intensity equal to here given, that point is very important now. What is the electric field intensity? 20 volts per cm is given. We can check once again. 20 volts per cm only. Yes. Now we can find. How we can determine the current here now? The current I can get from the what now? Current density, if you know, you can calculate. Current density equal to, you know very well, current by area. Current by area is nothing but current density in intrinsic semiconductor. I gave it already. In intrinsic semiconductor, we want. So current equal to, I can write J into A. Current density in intrinsic semiconductor into area only. If I know current density, I can determine the current only now. How I can get that Ji? You know very well. You know very well. The I can be calculated on a Ji current density can also be calculated by sigma I into E. J equal to sigma I into I. Conductivity into electric field intensity already given. Into area of cross section. That formula you can use. But a sigma I equal to 1 by rho I also we can write. Into E into A. Into A. Because the rho I we know very well. Already we got. Then I can find the current I. Electric field intensity given 20 volts per cm. Area of the cross section, what is given in the problem? Area is given as a 10 power minus 2. I can write 10 power minus 2. I can write. Rho I, just now we got it now. What value rho I? Rho I 2.31 into 2.31 into 10 power 5. I gave it already. 10 power 5 is not. Then that into what? 1 by rho I. But electric field intensity E, A I gave it. This is nothing but rho I. Finally, current is 0.864. 864 microamperes mostly possible. Yes, that much current is possible. From this we can say. In that way, we can calculate the value of current also. Understand my point now? Yes, we got. But a few more formula, what now? Certain parameters also required from the intrinsic semiconductor now. I would like to give certain formulas will come into picture here now. Intrinsic concentration. Intrinsic concentration. Intrinsic concentration. Intrinsic concentration symbol I gave it Ni. Already I gave it Ni. N suffix I is nothing but the intrinsic concentration. But intrinsic concentration in intrinsic semiconductors, what I said now, Ni equal to N equal to P also I said in intrinsic semiconductor now. It is the concentration of the free electrons or holes in the pure semiconductor. We can write it is the concentration of concentration of electrons or concentration of holes. We can write anyone. Concentration of holes. Concentration of holes also we can put. That is allowed. So N equal to P equal to Ni. That is why concentration of the electrons or concentration of the holes also we can write it below. It's not a mistake. Understand now. But how the intrinsic concentration is calculated in the problems generally, that value will be calculated like this only now. Ni square equal to, they will apply generally. Directly I can write now. A naught into T cube e power minus Ez naught by Kt they will use generally. By using this formula only, it is determined only now. T is the temperature, Ez means forbidden energy gap at 0 Kelvin. K and K is the constant, we know Boltzmann's constant comes out. T is the temperature, A naught is the constant you will give in the problems only now. Understand now. By using this, you can find mostly now. But the Fermi level in intrinsic semiconductors sometimes you will ask. Fermi level. Fermi level in intrinsic semiconductor. The Fermi level means exactly how we can define. Very simple way I will give the now. I will not confuse any students who know. Simple way I want to give now. The center of gravity which lies in between the valence and conduction band for electrons and holes is called as a what now? The Fermi level only we can say. For example, you have taken the balance, one balance you have taken. One side you got what now 5 kg, other side you got the what now 5 kg. Where exactly center of gravity is going to lie means exactly the center only now. The center of that balance only is going to exist only now. Suppose I have taken what now 15 kg, one side I have taken left side 15 kg, right side 5 kg I have taken now. Where center of gravity will lie? Very close to the what now? Higher mass it is existing only now. But like that, what you can say that center of gravity is going to change based upon the concentration only you can say. But in intrinsic semiconductor, we know very well concentration of electrons and concentration of the holes are equal. Then where it can lie, you can identify clearly now. Understand? In intrinsic semiconductor, what you have to understand, first of all, that energy band diagram I will draw here now, clearly now. Energy band diagram, it comes like this. This is nothing but the conduction band. This is nothing but the valence band. This is the valence band only now. But this energy is called as what you can say valence band energy. EV value they will put valence band energy. This voltage we are going to call it as a what? Conduction band energy only now. EC to infinity it goes. Here minus infinity to EV only possible for the valence band only now. This gap we are going to call it as a forbidden energy gap only we can say now. But in intrinsic semiconductors, concentration of electrons and holes are equal, everybody knows. Based upon that point only now, intrinsic Fermi level will be calculated only now. What I wish to say, for intrinsic semiconductors, we know very well. For intrinsic semiconductor, concentration of electrons and concentration of the holes are equal. Both are equal only now. We know very well, N equal to P only now. But N equal to what now? Concentration of electrons will be calculated by N equal to one formula is there. Nc into one formula is required. Conduction band coefficient Nc into e power. This formula you must remember. E power minus of EC minus EF divided by KT. That formula they will apply. But concentration of the holes are calculated by NV into e power minus of EF minus EV. EV by KT they will find. The calculation of the concentration of the electrons and holes will be done by these formulas only, the electronic devices. Once again, I will check this. EC equal to NC into e power minus of EC minus EF by KT, correct. P equal to NV into e power minus EF minus EV by KT, exactly correct. NC means what is the meaning? Conduction band coefficient they will call. But in the problems you will see, whenever you are going to enter into the depth, you will know what is the formula for NC and everything will come. In the foundation, we cannot do all those things. Just certain formulas directly I can give. Understand? If it is a classroom means we can derive everything now. Clearly we can derive this now. The NV means valence band coefficient only now it is called. EC is nothing but the what now? Energy, conduction band energy here. EF means Fermi level. We can find. Now I can write here clearly. I can write like this. I can write like this now. But N equal to P. N is nothing but what I can write? NC into what? E power minus of EC minus EF by KT. EF means Fermi level in intrinsic semiconductor. EFI I will put. Wherever EF is there, I will put EFI by KT. That equal to what? P. P is nothing but NV into what? E power minus of EFI, Fermi level in intrinsic semiconductor, minus EV by KT I can write here now. By KT I can write now. And NC by NV equal to how much I asked? NC by NV equal to how much? I can bring e power minus of EFI minus EI by KT divided by e power minus of EC minus EFI by KT we can write now. By KT it comes up. Like that NC by NV value possible. But this the denominator I want to take to numerator now because the KT is there now. It is a common for both. I will write here NC by NV I can write NC by NV I can write e power KT is common for both. KT is common for both. I can write here now minus EFI. Next, what I'm having? Minus plus EI, EFI minus E, what is the value? EB only, sorry, this is a EB, valence band energy, this is a EB is there now. EFI minus plus EV, I can take it now. And also we got whenever it goes to numerator, minus becomes a plus EC minus EFI. EC minus EFI minus EFI. That's possible here now. That's possible here now. That value we are getting correct exactly. But here the EC minus EFI, EC minus EFI, yes. But the finally conduction band coefficient divided by valence band coefficient equal to what you can get here now. Minus EFI is nothing but the minus 2 EFI. You are going to find plus EC plus EV, EC plus EV by KT we are getting. That value we got. Take log on both sides. Ln of NC by NV equal to what I can use, this formula we can use. Log and E cancel, minus 2EF plus EC plus EV by KT I can get now. By KT is possible. That value we are getting. Finally, this whenever the cross product is made, I can get 2EF. EF means EFI only, Fermi level energy. 2EF plus EC plus EV equal to KT into what I can get, ln of NC by NV I can get here now. NC by NV possible. My aim is to find the EFI only now. So EFI equal to what? 2 EFI equal to 2 EFI. That equal to what I can get. If you brought an EC plus EV, EC plus EV, then still what is left? EC plus EV minus KT ln of what I can get? Ln of NC by NV I can get now. NC by NV possible. NC by NV. Is it correct? Once again we can say NC by NV. Yes. Now we can find the EFI value directly. What is EFI here possible? Fermi level energy we can find by using this formula. EC plus EV. Sorry, one is a EV. One is a EV here. EC plus EV minus something, and EC minus plus EV by 2, this 2 will come to down, minus KT by 2 into ln of NC by NV we can use it. By using this formula only, Fermi level energy will be calculated only now. That way it is possible only now. Understand now. But the information is required for the what now? Fermi level energy only. Still so many analysis, lot of information possible from the intrinsic semiconductor. But in the foundation course, it is not possible to explain all these things. If anybody wants to learn in depth of the what now, these semiconductors, they need to take the admission in the IMS GATE Academy. Then 100% purely they are going to get every analysis they will know. And also the problems of the maximum you can find only, we can say, understand now. Okay, we can close this class by this extent only. Thank you.